Hello and welcome back. There are two systems that we study in physics that can be used to emulate far more complex systems. And those two systems, one of which you saw last time, mass spring system, and the second system, the pendulum system. Understanding the mass spring system and understanding the pendulum system give you a lot of power and a lot of latitude as far as being able to try and simplify and emulate more complex systems. So this video will be focusing on the pendulum system. Recall one of our conservation laws we ran into a few videos ago, conservation of energy. Energy is always conserved. It can't be created or destroyed. However much you have of this stuff we call energy before a process is going to be exactly the same as the amount of stuff you have afterward. So energy is always conserved. And never a single violation of that. The types of energies we're going to be focusing in on this semester: kinetic energy, potential energy, and Q is heat energy. And then remember that when we sum kinetic and potential energies together, we just call that mechanical energy. So mechanical energy isn't an energy unto itself, it's just simply the sum of potential and kinetic energies. The two potential energies we're going to be looking at this semester are associated with the two conservative fields that we'll be focusing in on this semester: the gravitational field and the elastic field. And remember, the elastic field, we're going to be really looking in on springs mainly, and so we're going to substitute spring for elastic. And so these are the two potential energies we've seen. So now focusing in on the pendulum system, what I've drawn here is a pivot point up here at the top, and then there is a string of length L that is attached to a bob of mass M. So I pull this mass away from its equilibrium position. And where is the equilibrium position of the mass? Well, the equilibrium position of the mass is right here. So this is the equilibrium position for M. And notice that as I pull it away from its equilibrium position, what have I done? I have raised this mass a height h from its low point. So notice that I have displaced this mass a height h from its equilibrium position, and then I let go. So I have provided mechanical energy by doing work. Notice that I grab the mass and I displace it vertically in the gravitational field. I do work. I exert a force upward and I displace this mass upward. So I do work. So the work done by me to start the pendulum system, the work done by me is the force that I exert, and that's of course the force exerted against the gravitational field mg times how high I place it in the gravitational field. And I've defined that height as h here, and I'll move this just in case you don't see it as well, and I'll write h here. So I have displaced it a distance h in the gravitational field. So this is the work that I did. Okay, what did work do? It shifted energy from me. I lost energy. I'm tired. I lifted this bob up a height h. It shifted energy from me into potential energy in the gravitational field. So work is an entity that shifts energy around. So I lost energy by lifting the bob up a height h, and the gravitational field gained energy by having a mass now vertically elevated with respect to the lowest point it can reach. Okay, so another way we can look at this mass is by using forces. So if we look at the forces being exerted on this mass right here, we can see that there's a gravitational force, which is mg, which is always pointing into the center of the earth, and then there's a tension force being exerted by the string on the mass, and that's it. Those are the only two forces acting on the mass. And notice that as this mass swings, and it's going to swing, right? I'm going to release this mass and it's going to swing down. It's going to reach its equilibrium position, but it's going to then slow as it comes back up until it reaches its maximum extension again, and then it's going to repeat, and it's just going to keep oscillating, right? Oscillation. It's going to oscillate back and forth and back and forth. So notice that this is a piece of a circle. So this is circular motion. The mass is undergoing circular motion. It is swinging back and forth and back and forth. And what's the radius of the circle that it's swinging through? The radius of the circle is the length L, the length of the string, right? The center of the circle is at this point right here. So the radius of this circle that's being traced out, this piece of the circle that's being traced out by the pendulum bob as it swings back and forth or oscillates, has a radius L. So let's look at these forces. So notice that I can take these forces and I can break them up into pieces that act along the centripetal line and pieces that act along the tangential line. So let's call this one the centripetal line. This is the centripetal line because it points into the center of the circle. So this is the centripetal line. And this is the tangential line. This is the tangent to the path of motion. And I'm going to actually draw it right here. So here's the tangential line. If I take, you can see that the tension force is a radial force. In other words, it's always pointing along the radial line. And that's true no matter where the bob is. Okay? The string is always pulling so that the force is directed into the center of the circle. So that means it lies on the centripetal line. So the tension force is always a radial or centripetal force. It never changes to be tangential. It is always centripetal. What about mg though? Well, mg depends on where you are in the oscillation. Notice that where it is located right here, let's just call this angle theta, we can see that we have a piece of mg that is tangential, and then we have a piece of mg that is centripetal. So we'll call that mg centripetal, and we'll call this piece mg tangential. So we can break mg up into pieces that are contributing to the changing in direction part of the mass, and that's along the centripetal line, and the piece that is involved in changing the magnitude part of the velocity or the speed of the object. So you can see that the tangential piece of mg is pointing toward the equilibrium position. And as you let go of this mass, this is the piece of mg that is trying to restore the mass back to the equilibrium position. And notice that as the bob swings down, the piece of mg that is tangential gets smaller and smaller. And when the bob is down here at the bottom, then the forces acting on the mass are the tension force, which is directly upward, and mg, which is downward. And notice that at the bottom, both of those forces now do lie on the centripetal line. So there are no tangential pieces to mg down here at the bottom. So as the mass swings down from the highest point to the equilibrium position, this piece of mg is getting smaller and smaller, reaches 0 at this location. And now what happens is the bob is rising back up. Well, let's just take any point right here in the bob's motion. The tension force points into the center of the circle. It's always a centripetal force. So it's going to point into the center of the circle. So there's the tension force T and mg into the center of the earth. And now notice that we have now mg as the tangential piece pointing away from its, or opposite to its motion. So there's mg tangential. And here is the piece that's mg centripetal that lies along the centripetal line, this piece right here. And notice I could just move it over here if I would like, right? I'm just showing you that tip to tail, they do represent mg. So mg then, this piece that is tangential, as the bob starts rising up, this tangential piece is getting larger and larger, and it's pointed opposite to the velocity. So that means it's the piece that's slowing the bob down. This tangential piece of mg is slowing the bob down as the bob is rising from its low point up to the maximum displacement once again. And the piece that is centripetal is getting smaller and smaller as it reaches up to the top here. So now when the bob is at this location up here, we have the tension force, which is again pointing into the center of the circle. So here's the tension force. And then we have mg, which again points into the center of the Earth, and mg can be reconstructed again into a piece that is centripetal and a piece that is tangential. So there's mg tangential and there's mg centripetal. This piece of mg tangential is the reason that the bob comes back, right? There's an unbalanced force. And notice that at these endpoints, these two endpoints, remember that we can add all the forces that are centripetal together, and that's equal to the mass times the centripetal acceleration. And remember, the centripetal acceleration is the speed squared over the radius of the circle that an object is moving through. And at the endpoints, what is the speed when the bob reaches its two endpoints? Well, the speed is instantaneously 0. So if the speed is 0, then that means the centripetal acceleration 0. That means the sum of all your forces must be 0. So at these endpoints, I've got the tension force, and we've also got the centripetal piece of mg. Well, those two must add up to 0. So I need to have as much tension force this way as I have the centripetal piece of mg this way, so that those two add to 0, and the same at this other end point. Notice that's not true down here at the bottom, because v is not 0 down here, right? V is the maximum amount down here at the bottom. V is 0 at the endpoints, and v is maximum at the bottom. V is in between 0 and maximum as the bob is actually rising and falling. So we can look at all of this using those tools that we learned in the first 5 chapters, using Newton's laws and using free body diagrams and summing up forces. We can also look at the bob's motion using the energy analyses as well. So notice that while we do have something other than gravity acting on the bob, namely the tension force doesn't do any work. Why is that? Well, because the displacement of the bob is always tangent to this path, and the tension force is always centripetal. And the definition, of course, between tangential and centripetal is 90 degrees. They're always orthogonal or normal to one another. So that means the tension force is always perpendicular, orthogonal, or normal to the displacement. So the angle is 90 degrees, cosine 90 is 0. Tension force does no work. Tension force does no work for the pendulum. On pendulum bob. Because it's always at a right angle to the bob's displacement. So when we have the bob down here, we say, let's use y equals 0 as our reference point down here. So let's say this is y equals 0. That's our reference point. So when we pull the bob up some height h from its low point, we've done work, and we've provided potential energy to the gravitational field. So energy shifted from us to the gravitational field, namely the bob now has gravitational potential energy with an initial amount, so the PE, and I'll just say here this is the end point, is going to be mgh for the bob. And it doesn't matter which of these endpoints, right? The potential energy is the same. What about the potential energy at the bottom? Well, the potential energy at the bottom is going to be equal to mgh. What height are we above the low point? 0. So there is no potential energy at the bottom. So because the tension force doesn't do any work, then that means the only force doing work is the gravitational force. If the gravitational force is the only force doing work, then we can apply conservation of mechanical energy. So therefore, only gravity working and ME is conserved. Therefore, the mechanical energy at any point, the sum of potential and kinetic, is the same as the sum of potential and kinetic at any other point. So at the M point, all of the mechanical energy is in the form of potential energy. The bob is not moving at the endpoints. So the kinetic energy at the endpoints, 0. The bob is instantaneously at rest at these endpoints, and the kinetic energy at the bottom then must be max. So notice that this is another system that shifts the energy between potential and kinetic, potential and kinetic, potential and kinetic. There's 3 points at which the mechanical energy is all focused in on either potential or kinetic and not the other. And that's these 3 points that we've drawn here on the pendulum. So these 2 endpoints, all of the system's mechanical energy is in the form of potential energy. Down here at the bottom, all the system's mechanical energy is in the form of kinetic energy. And then in between these endpoints and the bottom, the energy is in both forms, potential and kinetic energy. So we release the bob starts to fall, H is shrinking, the potential energy is decreasing, the bob is speeding up, its kinetic energy increases. The bob reaches the lowest point, H is 0 here, and so there's no potential energy. The bob is moving the fastest here, it's all kinetic energy. The bob starts to rise, now H is increasing, the potential energy is increasing, the bob is slowing down, so the kinetic energy is decreasing. At the end point, all of the energy is in potential energy. So a system that just sloshes the energy back and forth between potential and kinetic energy. And this is a really nice system to look at both from the forces perspective and seeing, how you can draw free body diagrams and break this up into centripetal and tangential and analyze the motion that way, or by using the energy perspective and looking at the mechanical energy, because we are in the realm of mechanical energy conservation in that only gravity is doing work. So gives us a nice overview of a really important system, and understanding this system is imperative. So watch this video as many times as you need to make sure you have a really good solid understanding, and of course ask questions if you don't, and we'll see you next time.